Welcome to the UGC lecture series. In this lecture, we are going to talk about some of the operations of stacks using linked list, and we are also going to talk about some of the interesting applications of stacks, of which we are going to see two: the depth first search and the n queens problem. So, let us start with how stacks are represented. So, stacks are represented with a node in the linked list with the node containing data, that is what is to be represented, and a link pointing to the next node. And you can also have an access to the stack through a node which is designated as top, and you can also maintain a count of the number of elements in the stack. Now, the first thing that we are going to do is we are going to create a stack. For creating a stack, you have to first dynamically allocate a stack whose size is equal to the size of the stack, and if the stack top is equal to null, then that is what we are doing to initialize the top, and we are also, since we are just creating a stack, you are initializing the top to be equal to null and the count to be equal to 0. We have not yet actually created a node. Okay. This is the first step in creating a stack. So, once you have created a stack, we are going to do the operations on stack. So, the important operation, as we have already seen, is the push operation. This is, if you look at a linked list representation of a stack, the push operation is similar to inserting a node in the front of a list, because all the operations are done with the stack at the top of a, you can access the stack only through the top. The insertion and deletion, when you represent a stack as a linked list, is in the front. So, here same as inserting a new element to the list before the first element. So, let us assume that this is the element that we want to insert, and this is the previous stack. So, the previous stack has this is the count and this is the top. So, top is pointing to the first element in the stack. Now, you want to insert the new element. First, you have to create a node for the element, and this is the address of the node, and this contains the data read and a pointer next. So, that is what is available. Now, when you are going to insert this into the stack, it comes like this. Now, this is p new, and which we know is the address of this. You create the next, or change the next pointer to point to the address of blue, and you have to change two things: the top to point to the address of red, and you have to increment the count to be equal to 3. So, this is the insertion of, or the push operation. We do not call it insertion in stacks, we call it as a push operation, push into the stack, which is represented as a linked list. So, this is the push operation, the code for the push operation. So, first thing that we have to do is we have to create a node. Okay. Then in that node, you have to, for creating a node, you have to get it from the allocated area. If there is no allocated area, that is, you cannot get a new node, then you cannot insert. Once you have got that, in that new position, you put data to point to whatever the data you want to insert, and you make the pointer of the new location or the new node that you have just created to point to the original stack top, and now change the stack top to point to new pointer, increment top to point to the new node, and you increment the count of the stack by 1, and you return 1. This return 1 is to just indicate the success. So, this is what we do for insertion into a stack. This, as you can see, this is very similar to insertion into the front of a linked list. Now, let us look at the next operation of the stack, which is a pop. A pop is to delete the element, and as you know, you can only delete the element from the top of the stack. That is the constraint that you have on a stack. So, this is the same as removing the first element from a list, linked list. So, what you have to do is now this is the original stack. Now, the only element you can delete or remove from the stack is from and you do the pop operation is this element. There is no other element that you can remove. So, what you do is you make the top now point to blue, okay, and that is it. So, now you can access the stack only through this. Now, you have a node which is sort of dangling. So, this can be recycled. So, you make a pointer to point to this node so that it can be recycled. So, this is the pop operation. So, the code for the pop operation is as follows. So, you have a pointer to point to the node which you want to return, and if the stack, as we have already discussed, when you want to do a deletion, or when you want to you must first ensure that the data structure from which you want to do the deletion is not empty. So, that is what you are doing here. You are just checking the count to whether it is equal to 0. If it is equal to 0, you are saying that it returns 0, which means there is an underflow, there are no elements to be deleted. Otherwise, you make this pointer to point to the original stack top. This is for recycling purposes, and then what you do is make the stack top point to the new stack top, and you free DLT pointer. This is what you are going to do here is you are freeing the node that has been deleted and decrement the stack count and return a value of 1. So, this is the code for the pop stack. Both these cases the stack has been represented using a linked list, and this particular data structure is very useful when we are doing for organizing the nodes in an allocated list. It is called a stack allocation list, and that is represented as the linked list to store all the nodes that has been deleted, or when you want to delete you store the for recycling you take it into the allocated list, which is represented as a stack, and when you want to insert you take a node from this same allocated list. So, the next is stack top. As we have already discussed before, stack top does not change the stack at all, it just accesses the top element of the stack. So, again if the count is only greater than 0, if it is equal to 0, that means the stack does not contain anything, then you just take out this is a pointer to the top element, make that data to be returned in data pointer and return 1. If it is less than 0, that means there is no stack, so you return 0. So, that is the stack top. Here no changes occur in the stack. Then this is a normal thing, that is the empty stack and a stack count. So, what you do here is if the count is equal to 0, then you return that value, otherwise the stack is not empty. This is just a boolean code for a boolean function which is empty stack. It returns a value true if the stack is empty, returns a value false if the stack is not empty. This is to return the count. So, you already have maintained the count. There are implementations where you do not maintain the count of the stack, certain implementations you do maintain the count. So, return stack count, that is it. So, the count can be 0 if the stack is empty. You can also check for full stack. Now, this is assuming that you have decided that only so many nodes that you are going to give for the stack, this is that. So, if you have a stack full condition, then the malloc has failed. Then if the malloc has failed, it means that you cannot there is no temporary node to be given for the operation, in which case you have a return 1. So, this is a full stack where you cannot remember that in a full stack condition we are checking whether there are nodes available for putting into the stack. If there are, then we are not saying full, otherwise we are putting full. This is not like an array implementation where we already allocate the nodes, the size of the stack. This is for destroying the stack, that is destroying the complete stack. So, you want to delete all the nodes in the stack. So, if the stack top is null, it means already that the stack is empty, you do not have to do any destroying. So, if it is not null, then you make delete pointer to point to the top of the stack point to the next element, next node, and free delete pointer. You keep doing this till the stack becomes null, that means you have come to the last node in the stack. The stack is now empty, then you have to destroy the head node. So, free that and you return null. So, this you are having a while loop here, this is the logic where you keep on deleting nodes or popping out nodes till the stack becomes empty. So, let us now what we have seen up to now is the some of the implementations of stacks where we have looked at the linked list implementation of stack. In this particular implementation of stack, what we have done is we have assumed that you have a count also, it is not necessary. So, in case you do not have a count, then the code has to be appropriately modified. Now, let us go to the next. Some of the applications of stack were very interesting applications, and stacks are used in a number of places in computer science itself. For example, the stack is a specific data structure that is used for the quicksort algorithm. It is a typical data structure. It is also used in other applications like very important applications where you have to maintain the program counter and the return address in the case of recursive calls or function calls. So, this is a very important data structure as far as computer science is concerned. We are looking at two very different applications. One is the depth first search and one is the n-queens problem. So, let us first look at the depth first search. So, depth first search is actually a backtracking type of concept that it uses, and for this backtracking type of concept we do use a stack. The stack is a typical data structure that is used for doing the backtracking. So, the problem is as follows: discover a path from the start to the goal, and the solution you have to go deep. If there is an unvisited neighbor, go there, then you retreat along the path to find an unvisited neighbor. The outcome is, if there is a path from the start to goal, DFS will find such a path. So, this is it, that is you are going to go deep and you are not going to go breadthwise, that is the idea. So, this is a typical application of a stack. So, let us assume that we have given a tree and we want to find the goal. So, initially you start with 1 that has been pushed onto the stack, then you go to 2 depth, you remember. So, go to the child, so push 2, then you push 5. Now, 5 has no children, so you go to the sibling which is 6, then you go to its child 9. Now, after that you do not have anything, so pop it out, pop 6 out, then pop 5 out, pop 2 out, then you go to the next child which is 3, then you go to 7, then you go to 10, that is the depth first. So, you go to 10 and now you have identified the value. So, the path followed is 1, 2, 5, 6, 9, then you backtrack up and then you go to 1, find the next child, go down. Okay. So, this is the path that is followed for the depth first search. So, let us look at the algorithm for the depth first search. So, the stack is first initialized and you start the operation with S push start. Now, while the stack is not empty, this is to keep track, you take out the top element. If it is the goal, you just put success. If T has an unvisited neighbor, choose an unvisited neighbor n, mark n as visited and push n into the stack. Otherwise, that is if it does not have an unvisited neighbor, then you backtrack, take the next node from the stack, keep doing this till the stack is empty or you have reached a goal. So, this is the depth first algorithm. Of course, when you are searching for a node in the depth first algorithm, you can also happen that there may be a failure. So, this is a typical application of stack where the stack is used to maintain the nodes when we want to do a depth first algorithm, especially a backtracking algorithm. This is a typical data structure that you use. Many concepts that use backtracking also use stack as its basic data structure for implementation purposes. Now, we are going to look at what is called an n-queens problem. This is a typical problem in artificial intelligence, and the n-queens problem is actually a problem associated with the chessboard. So, in this lecture I will explain the problem and then see how it is solved using the stack. Okay. So, first let us see what the problem is. The n-queens problem can be defined as follows. It is a backtracking problem to solve the n-queens. Suppose you have 8 chess queens and a chessboard. Can the queens be placed on the board so that no 2 queens are attacking each other? Now, what do you mean by this attacking? We will see that as we go along. So, the problem is this: 2 queens are not allowed in the same row or in the same column or along the same diagonal. So, that is the idea. So, 2 queens are not allowed on the same row, on the same column or along the same diagonal. The number of queens and the size of the board can vary. Normally, you solve this problem for an n-queens problem. We are going to take a simple example and show you, but basically you can solve it for any queens. After all, the chessboard is a square. So, you can have a 64 into 64 where n is equal to 64 and so on. So, basically the n queens can be represented in this way. It consists of n queens and the chessboard that you have consists of n rows and n columns. So, your aim is to place these n queens on the board such that if you have a queen here, you do not have a queen anywhere here. If you have a queen here, you do not have a queen anywhere here, and you also do not have a queen anywhere here. So, you cannot have 2 queens on the same diagonal, on the same row, or I am sorry, on the same column or along the same row. So, that is the problem. So, our idea is to try to find a solution to this problem, a computer program to solve this problem. The program tries to find a way to place n queens on the n into n chessboard following the instructions that we have already seen. So, now comes the application of stack. We are going to use a stack to keep track of where each queen has already been placed. So, first you place a queen on the board. The position of the new queen is stored in a record which is placed in a stack, and you also have an integer variable to keep track of how many rows have been filled so far. So, these are the 2 things that you are going to use to keep track of how to place the n queen. So, this is how the program works. you have a, so we have taken a 4 into 4 board, a very simple example to show the how the program works, and this is the number of queens you have to fill, which is 4, and this is the stack that we are going to use. The stack contains a record which gives the position of the queen, which is 1 1 means this is the position, 1 2 means this, 1 4 means first row, fourth column, and so on. And this is a variable which keeps track of how many queens have already been placed. Okay. So, this is that variable. This is the complete. So, you have a n into n board, you have n queens, you have a stack which gives the position of the queen, and you have the number of queens that have been placed correctly as the program. Now, let us start program. So, first you place 1 here, okay. Then you come to this, what happens? So, that is 1 1 has been placed here. Then you come here. Now, can you place a queen here? You cannot place a queen here because it is along the same diagonal. So, the logic uses that you shift it once to the right and see whether it breaks any of the rules. Now, there is no queen along the column, there is no queen along the row, there is no queen along the diagonal. So, this is allowed. So, now you have a queen at 1 1, you have a queen at 2 3, and 2 have been filled. Now, we have to place this queen. Now, can you place it here? You cannot place it here because it is in the diagonal. So, 3, so what you do is you go up here and you place it here. Can you place it here? 3 4, 3 4. So, third row, fourth, you cannot place it here because of the fact that it is along a diagonal. So, how the program works is when we run out of room in a row, pop the stack, reduce filled by 1 and continue working on the previous row. Let us look at that. What this means is when you cannot place, pop it off, go to the previous row and see whether you can place it along the right or left. We will see the logic of this as we go along. So, again I will tell you, when we run out of room in a row, pop the stack, reduce fill by 1 and continue working on the previous row. So, whatever was placed in the previous row we are removing. Okay. So, that is what happens here. So, this is our position, we still have 2 queens to do, and we have reduced filled by 1. Now, we continue working on row 2, shifting the queen to the right. So, now instead of us having it here, we have popped it out and we are shifting the queen here, and now this has to be incremented. This position has no conflict, so we can increase fill by 1 and move to row 3. So, now we will move to row 3. Now, in row 3 what happens? We cannot place it here. Can we place it here? Yes. We cannot place it here because it is a diagonal. So, we place it here. Position has no conflicts. So, 2 has been filled, and then we go to 3 1, but this is a conflict. We start again at the first column, conflict, second column there is no conflict. So, that is how we go along doing the problem. You can work it out on your own and see how the 4 queens are filled. So, the logic basically, to repeat, is you take a row, place a queen there, then you go to the next row, place a queen there, you go to the next row, place a queen. When a conflict arises, what you do is you try to push the queen to the right if it is possible and no conflict arises. Now, if you come across a conflict, then you pop the top element from the stack, that is you are backtracking, you are not using that. Okay, what you have already placed you are removing from the stack. You remove it and try again to rework on the previous row, and that is how you do the n queens problem. So, for our n queens problem, let us see, this is a slightly different problem that we normally use. So, in this we are first going to talk about the pseudocode. So, here what we do is we first initialize a stack, which is the data structure we are going to use to keep track of our decisions, and we also place the first queen, pushing its position onto the stack and setting filled to be equal to 0. Now, this is the pseudocode. You repeat this step. If there are no conflicts with the queens, then you do, else if there is a conflict and there is room to shift the current queen rightward, do that. Else if there is a conflict and there is no room to shift the current queen rightward, then what you have to do? You have to keep on doing this, repeat this. There is no conflicts, increase fill by 1. If filled is now what I am doing here is I am taking each of these steps and giving the details. So, if there are no conflicts with the queen, what do we have to do? We have to increase fill by 1. If filled row is now n, that means you have filled all the queens, then the algorithm is over. otherwise move to the next row and place a queen in the first column. So, that step is over. So, what we have done is we have done this, we have taken the queen, okay, we have placed it in the first in the row, we have seen if there is a conflict. If there is a conflict, you are moving it right. Okay. If there is a conflict and there is room to shift the current queen rightward, move the current queen rightward, adjusting the record on top of the stack to indicate the new position. Okay. So, this is in the same row. Now, even that you cannot do, you are in a position where you cannot fill, there is a conflict, cannot move rightward and fill because there is a conflict again. Then if there is a conflict and there is no room to shift the current queen rightward, this is the place where you have to do the backtrack. Okay. So, what you do, you keep popping the stack and reducing the fill by 1 until you reach a row where the queen can be shifted rightward. Then you shift this queen right. That means what you are doing is whatever work you have done before, you are backtracking, okay, and you are backtracking till you reach a position where you can have another alternative, which is not placing it there, but moving it to the right if it is possible. So, the movement to the right is one step at a time, but it may move to more than one also. So, that is the n queens problem. Now, why the n queens problem is really challenging is that we are actually redoing the work that we have already done, so that we get a choice of what we do actually in this algorithm is we first start with the easiest method, we place it in the first row that we see. Then we keep on doing it till there is the second also we take an easy way out. Okay, when I place it in that place there is a conflict, so let me move it right and see. Now, if I move it right and see still there is a conflict, only then I go back and I check whether what I have initially done can be changed so that this can be accommodated. You can probably try this for a 6×6 or 4×4 on your own, simulate it and then see how it works. That will be a good exercise for you when you for you to understand how the stack works and how a backtracking algorithm works also, because this explains both the concepts of backtracking as well as the application of stacks to backtracking. Now, let us look at some problems associated with stacks. Now, we have up to now we have seen array implementation of stacks and all that. It is possible to keep two stacks in a single array. Now, if one grows from one position and the other grows from the last position, we want you to write a procedure push x comma s that pushes element x onto the stack s, where s is one or other of these two stacks. Actually, you have to put here si, that is it can be I can be 1 or 2. Now, you have to include all necessary error checks in your procedure. This problem, if you write the code for this problem, is interesting for the following reasons. One is that you have what is the stack full condition. Now, is a stack full condition, okay, one way of doing it is without being dynamic is you have an array, okay, and you say that let us say an array of size 100. Then you say that 50 is allocated for stack A and 50 is allocated for stack B. So, if you reach the 50th position, you say this stack is full. If you reach the 50th position from the back, then you say this 100 to 50 one stack will grow from 1 to 50, that is fine. But then that is not interesting, because you are using a single array to store the two stacks. So, suppose let us assume this stack is only occupied 10 positions, but that stack is occupied 50 and is crossed, but actually there is position in the array for storing elements. So, we can modify our stack full condition accordingly such that you will get a stack full condition only if the complete array is occupied. It is an interesting exercise to do. Another interesting exercise that we can do for stacks, which is the elimination of to eliminate recursion from the procedures, and this is very important application of stack in data structures. So, this is a function that we have got, and you can try to use a stack to eliminate recursion from this. If you note, this is the recursive call that you have two recursive calls, one recursive call here and one recursive call here using the same function. So, you will have to write an algorithm to eliminate recursion from this. You have another algorithm also called reverse, where again this is the recursive call. So, try to write a stack to eliminate recursion from this. So, here what we do is instead of using reverse L, we are going to eliminate this by using a stack and eliminating the reverse operation. So, in this lecture we have looked at the linked list application of stacks, and we have seen the typical applications of stacks also. So, the linked list implementation of stack, we saw the typical algorithms, the creation of a stack, the push operation, which was, as far as the linked list was concerned, insertion into the front of a linked list. We saw the pop operation, as far as linked list is concerned, was deletion of the first element of a linked list. Then we saw the top, where we did not change the stack, we just took the top, accessed the top element. Then we saw a Boolean function called empty, where it showed whether the stack was empty or not. And then we had a full condition, where we checked whether the stack is full or not. This makes sense normally only for arrays, but in this application, in this implementation, we assume that some amount of nodes are available for the stack to use, and if the nodes have all been used up, then we say a stack is full. We also saw a destroy stack, that is destroy all the elements of the stack. Then we saw some two important applications of stacks. One was a typical backtracking application, which we also saw before for queues, where we used it for breadth first search. But the other application, where the NQueens application, was very interesting, because we used that for the concept of backtracking, where work already done is again redone by keeping track of what was done through the use of a stack.